Questions that you've attempted that perhaps you struggled with? Number 11. Okay, we can talk about 11. Yeah, Alana? 4? Okay. 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 Dwayne and Colden, how we doing back there, guys? Kai, Kale, we good? Okay. Okay, so there were 2 questions about the homework I assigned. Questions 4 and 11. If there are others, let me know. But I'll do we can go over these 2. Number 4 says to calculate the gravitational force on a 6.5 times 10 to the 2 kilogram. Presumably that's a mass. That is 4.15 times 10 to the 6 meters above the surface of the Earth. So we want the gravitational force, Fg equals, and we are pretty far above the surface of Earth, so we can't just use Fg equals mg. We have to use universal gravitation. So that's the expression we're going to use, and we're just going to plug everything in. We don't know Fg, that's what we're looking for. Big G is 6.67 times 10 to the negative 11. Big M, it's being held above Earth, 5.98 times 10 to the 24. The mass of the object, we're told, is 6.5 times 10 to the 2. So GMM, and then we want that to be over R squared. R is, you got to remember, R is the distance from the center of one object to the center of the other object. And we know the radius of Earth is 6, what is the number? No, where's my formula sheet? Because that number's on there. 6.38 times 10 to the 6. We also know this distance here from the surface of the Earth to the center of our object is another 4.15 times 10 to the 6. So the total distance from center to center is the sum of these 2 objects. Or sorry, of these 2 distances. So then that R value down on the bottom is going to be 6.38 times 10 to the 6 plus 4.15 times 10 to the 6. And that's R squared in the denominator. So this is the thing that you're punching into your calculator. Alana, is that enough? Okay. That's question number 4. Okay, question number 11. I did give you a fair bit yesterday. There's object A, there's object B, there's object C. We're given these distances. 50 centimeters is 0.5 meters. I'm going to make that adjustment right away. This has a mass of 10 kilos. This has a mass of 10 kilos. This has a mass of 15 kilos. And we want the net force on object B. So this guy's going to have a force to the right, Fg from C. And it's going to have a force to the left, Fg from A. They're left, right, they're opposite directions. So we need to declare a direction to be positive. Yesterday you said you wanted positive to be to the right. So when we plug this thing in, we're going to have Fg from C rather, because that's the one that's to the right, minus Fg from A, and that's going to be your F net. If it wants the net force, that's just the sum of the forces in the direction of motion. So that's just going to be MC MB over R squared minus big G MA MB. I'll label these different. Over. I'll call that RC squared. I'll call this RA squared. And at this point, we're just plugging in values. G is 6.67 times 10 to the negative 11. That mass is 15. That mass is 10. That mass is 10. That mass is, sorry, that mass is 10. That mass is 10. This distance is that distance, 0.5 meters. This distance is that distance, 0.5 meters. You run it through your calculator, and there's an answer at the bottom of your page. That should be 1.33 times 10 to the negative 8. Hey, Rem, is that enough? Okay. And then to find the acceleration of object B, this is going to be F net. So that's what the question is asking for. The part that I added was, what's the acceleration of object B? Well, F net equals ma. So you're going to get this value, 1.33 times 10 to the negative 8. We want the acceleration of object B. So that's going to be the mass that's going to go in here. That's going to be 10 times a. So then we're just dividing both sides by 10. That's just going to lower that exponent. It's going to be 1.33 times 10 to the negative 9 meters per second squared. So a just absolutely minuscule acceleration, but it's not zero. You will, if these three things were set out in space somewhere, you would start to see this thing drift towards C. But that would get complicated because A would start to drift towards C as well, and C would start to drift towards A and B. If they were just out in space, they would start to come together. So that's 11. Well, and 4. Are there any other questions anyone wants me to at least sort of go over? There was a particularly good question. Oh, Ray, where was that question you asked me yesterday? Was it number 3? Yeah. The gravitational force between objects of equal mass. Do anyone have questions about 3? 3 is a good one. Or we follow the trick on 3. Okay, if you haven't had a chance to look at 3, please do. There is an important word here in 3. The important word is that those masses, the objects of equal mass, that word equals really important. So if you haven't had a chance to look at 3, definitely do that. If there are no other questions, then let's take a look at today's stuff. Okay, where are my notes for today? These guys. Yes, now you may go. Okay, find me this page, gravitational field strength. It is a subset of what we looked at yesterday. And I'll show you where it comes from. So we talked about gravitational field strength a bunch. When I gave you guys this formula, F equals mg, I originally told you that this value, or this lowercase g, on or near the surface of Earth had a value 9.8 meters per second squared, or 9.81, meters per second squared. In kinematics, we dealt with it as an acceleration. In dynamics here, the way I introduced it to you was that this was a gravitational field strength. And then in yesterday's lesson, I tried to make the argument that gravity depends on the masses of the two objects and then how far away you are. And I gave you this formula here. So that should be Fg. I said, okay, well, Fg is equal to g mm over r squared. And I said, well, this is also equal to the force of gravity. So if I have two things equal to the force of gravity, and if what we said yesterday is true, and that gravity changes based on where you were, and when I qualified this, I said very specifically that this lowercase g was at or near Earth's surface, then I should be able to make a statement that relates these two equations together. If the force of gravity is equal to the mass times the mass of the object experiencing a gravitational field times the gravitational field, but gravity is also equal to gmm over r squared, where one of these masses is the mass producing the gravity, and one of these masses is the mass experiencing the gravity, then what here should I be able to set equal to each other? You can't have two things being equal if you can't make a statement about their individual parts being equal. Take a look at what we've got here. I've got a mass that's being acted on by a gravitational field, and I've got a mass that's being acted on by all of this. If this little m and this little m both represent the mass being acted on by gravity, what can we say about the rest of the equation? Anyone want to make an educated guess? Sire, you look like you do. That's exactly it. Little g, which we said was gravitational field strength, has to be defined as big G times big M, the mass creating the gravity, divided by r squared. And so now what this is going to give us is, if little g represents gravitational field strength, this portion of the equation is going to give us what that strength is anywhere around a given mass. So this is now defined as, this expression here is defined as the strength of gravitational field around some mass, which we will call big M. And the idea that I use to kind of help this make sense is this over here. To help explain how two bodies that are not in contact can exert a force on one another, we use the concepts of fields. There's a few fields that you're going to talk about if you go on and continue to study physics. This is the first one. The gravitation, the idea that masses have gravity or create a gravitational field around them. The second one that you'll look at is what's called an electromagnetic or electrostatic field. The idea that a charged object has a field around it, a static field around it. And then the third one that you'll look at is a magnetic field, which you've hopefully had a chance to play with over the course of your life already. Playing with magnets is some of my children's favorite things to do. How we define fields are spheres of influence. They're invisible. They're not tangible. It means we can't manipulate them. They just demonstrate how strong a characteristic is at a certain distance. So consider a campfire. You guys should all be familiar with campfires. You can think of it as having a heat field. The closer you get to the campfire, the stronger the field becomes. Even though there's not actually anything tangible there, as you get towards it, you can feel the intensity of the heat increasing. Just like gravity. Even though there's nothing actually there, it's not like there are particles of gravity pulling you in. The closer you get to the source of the gravity, the stronger it's going to affect you. And likewise, the larger the fire, the stronger the field. It's the same way with gravity. The larger the object, the stronger the field. So now we've got a definition for gravitational field. And you don't actually need, it's like the age-old question, if you are walking in the forest, if a tree falls in the forest and there's no one there to hear the sound, does the tree make a sound? If there's nothing there to experience a gravitational field or a heat field, is it actually there? And debate that forever. But that's effectively what this is generating. It's telling you how strong the gravitational field would be if you placed an object at some location around another object. If you take a look at the units on this thing, originally we said that g was an acceleration, and accelerations have units of meters per second squared. But if you look at this piece here, this piece of the equation is equal to, well, it is this piece of the equation. So if I wanted to isolate for this, what would I have to do? How could I get gm over r squared by itself? How do I get these three terms to stay together and get rid of everything else? What else is here for there to move? Well, the only other thing is that little m, yeah? How would I get that little m over to this side of the equation? How is that? Yeah, Brad. Yeah, just divide it over. So what we get here is the idea that little g is equal to gm over r squared, but that's the same as fg over little m. And let's look what these units are. What are the fg is a force. What are the units of force? Sorry? Newtons? Yeah. What's the units of mass? kg. So when we talked about gravitational field strength, we can talk about as having either of these units. The strength of the gravitational field is either going to be measured in meters per second squared, based on the kind of acceleration it causes, or we could say that the strength of the gravitational field is measured in newtons per kilogram, based on this much force per kilogram of mass. Yes? Mm-hmm. I thought does that mean mg is equal to that whole thing? Mm-hmm. And then I took the m from mg, and then it's multiplying with the g and mg, right? Mm-hmm. And then I divided it, I moved it to the other side, and I divided it with the m on the other side. That's correct. But that's absolutely a way to talk about this. There are physicists everywhere that would freak out about what you just did, because technically speaking, these two m's represent different quantities. Like these little m's, they represent different conceptual ideas. So if you did that if you showed a physicist out there in the world, yes, this is what I did, they would say mathematically that makes a lot of sense. But can you prove to me that little m, inertial mass, and this little m, static mass, can you prove to me that these two little m's are the same for a given object? We can, but there's a reason why I didn't do it that way. Because I'm trying to make the argument that these are equivalent without doing that. Because if you can make the argument that little g and gm over r squared are the same without doing that, you can prove that these two little m's are the same. And at this stage, it might feel like that's a pointless argument to make, but in the grander scheme of physics, you can't assume that that's true. But what you did, the mathematicians out there say, of course, yes, great, love it, do it. Every time, that's perfect. So I will tell you this now, and I tell every semester this. I am going to give you guys, on your unit test, I am going to ask you to calculate for me forces due to gravity and gravitational field strength around an object. Those are not the same thing. They're given to you differently on your formula sheet. And every semester, about half my class forgets the difference between these two quantities. If it has an F, it's a force. That's why I've been so deliberate about labeling everything. Fg is a force. Ft is a force. We're going to talk about force of friction. Ff is a force. Normal force is Fn. That F is there for everything. If it's not, you're not calculating a force. So this little g here, this is the one that you got to remember. It's not a force. It's the strength of this concept, little g, and little g is gravitational field strength. They're fundamentally different. Don't forget that that's going to be a thing. And now I'm curious to see how many of you do. So I'll do a couple examples of this just to show you how it works, and then you'll have the rest of the block to play with. Well, and then we're going to talk briefly about satellites, and then I'm going to leave you the rest of the block to play with this stuff. So here we go. Example 1. The Earth is not a perfect sphere, believe it or not. No, I'll leave it at that. It's not a perfect sphere. Just like a spinning basketball. So if you took a basketball and you started to spin it really fast, different parts of the ball are experiencing things differently. I can't do it, so I'm not going to even bother trying. But I've got a volleyball here. I can't spin this thing on my finger. I've never been able to do that. But if you think about this object, if it starts to, as it's stationary here, all parts of the object are experiencing its existence the same way. But if you start to spin this object, if it starts to spin faster and faster, the top and the bottom of the or volleyball, in this case, I think that question's in basketball, this is volleyball. As they spin faster and faster, the top and bottom aren't going anywhere. They're stationary. But the middle part is actually spinning quite quickly. And so as you spin this thing, just like the Earth spins, what do you feel when you get spun? Have you ever been on a merry-go-round? And not even, sorry, I shouldn't say merry-go-round. The death trap that is like the old school playground merry-go-rounds, you get on that thing and your friends just kind of crank it and spin. What do you feel like? It's awesome, but it's horrifying. You feel like you're going to get flung off the seat sideways. I mean, the Earth is doing the exact same thing. As it spins, because the top, and if you were standing in the middle of the death trap as it spins, you just do this. There's nothing that's trying to launch you one way or the other. It's the further you get from the middle that you start to feel like you're going to get thrown more and more. The Earth is doing the exact same thing. The top and bottom, the North Pole and South Pole, they just spin. But as you get down to the equator, as the Earth is spinning, it's spinning quite quickly. And so all of the land around the equator bulges out. So what that does is it actually creates an Earth that looks more like this, where you get a slightly flatter pole on either the top and bottom, and a chubbier middle section. It's called an oblate spheroid. We don't notice it because the Earth is so large, but it's there. So we can what that means is the Earth is fatter around the middle and thinner at the poles, so we can calculate the gravitational field strength at the North Pole and at the equator and compare them to each other. So that's what this example is asking us to do. Earth is chubbier at the middle, so there's more Earth there. So let's see what the gravitational field strength is at the equator. Let's do the second one first. If I wanted to find the gravitational field strength or acceleration due to gravity means the same thing, this is equal to gravitational field strength. I'll do the equator first. This is the value for the average value for the radius of the Earth at the equator. So just to show you what this value looks like, because sometimes scientific notation is hard to picture, this is 6,386,000 meters. So if I wanted the gravitational field strength at the equator or the acceleration due to gravity at the equator, I would say that G is equal to G big M over R squared. And these are values for the object creating the gravity and how far you are from its center. We'll say little g is then going to, well, big G now is 6.67 times 10 to the negative 11. The mass of the Earth has not changed. 5.98 times 10 to the 24. But now we're not 6.38 times 10 to the 6 meters from the center. We're 6.386 times 10 to the 6 meters away. And we can't forget to square that R value. If you punch that into your equator, into your calculator, what's the acceleration due to gravity or the gravitational field strength at the equator? As soon as you got a value, let me know what it is. Yeah, Ezra. Is that rounded to 2 decimal places? Okay, so 9.7, yeah. So yes, that is rounded to 2 decimal places. 9.78 meters per second squared. Cool. So that's at the equator. Means technically speaking, at the equator, you actually fall slower than the value that we've been using so far. Okay, let's do the other one. At the North Pole, because of the spin of the Earth, you actually get a squished bit, though that I tried to argue earlier. So let's figure out the acceleration due to gravity or gravitational field strength there. That's going to be, the equation is the same, gm over r squared. Big G is 6.67 times 10 to the negative 11. Big M is the mass of the Earth. That hasn't changed. But now this value is 6,370,000. Now we're going to square that. Look at the difference here. This is a difference of 16,000 meters. More, I mean, maybe it's more useful to think about it this way. This is 16 kilometers. So what this means is the Earth is actually 16 kilometers shorter at the poles than it is at the equator. That's not an insignificant value. What's the value for G at the North and South Pole? Ezra. Oh, is that rounded? 9.829. So we're going to round that to 9.83 meters per second squared. Because you're closer to the center of mass of the Earth at the poles, you're actually going to fall faster at the poles than you would at the equator, which is weird to think about. Just for fun, let's take the average of these two. How do you take the average of two values? Add them together and, yeah, as many values as there are. So what's the average of these two values? Add them together, divide by 2, and you get that the average G is going to equal what? Is it exactly 9.8? 9.805, which rounds to what value? 9.81 meters per second squared. This is why this is the value we give you, because it is the average acceleration due to gravity. If you took all the locations on the Earth and averaged them up, this is the value you'd get. Technically speaking, there are locations on the Earth that will have higher or lower values depending on where you are on the planet. But we use this value because this is the average, and in the grand scheme of things, what's plus or minus 2 centimeters per second squared is effectively what that is. It's not going to give you, in the grand scheme of you living your life day to day, dropping objects, it's not going to give you a noticeable difference. But the difference is there, and it's real, and it's measurable, which is kind of weird to think about. Questions about what we've just done? Okay. Another concrete calculation example. Here it is. The moon. The moon is 385,000 kilometers away from the Earth's surface. What is the gravitational field strength at this distance? So how strong is the Earth's gravitational field way the frig out where the moon is? Let's figure it out. Here is Earth. There's the moon. The way the question is worded is it says the moon is 385,000 kilometers away from the Earth's surface, and we want to find gravity out here. Gravity is always measured from the center of one to the center of the other. So we don't want surface to moon, we want this whole distance here. This little piece is the radius of the Earth. We know that value. That value is what? Well, 6.38 times 10 to the 6 meters, or 6,380,000 meters. And this value in the question we're told is 385,000 kilometers. But if this is in meters, and this is the kind of stuff I'll do to you, if this is in meters and that's in kilometers, what should we do first? Change everything to meters. So how do I take 385,000 kilometers and put that into meters? What do I, sorry? We're just going to add 3 more zeros, you bet. So this distance here is going to be 385,000,000 meters. 385 million meters. So the radius of the Earth is 6 million meters. The distance from the center of the, the surface of the moon, the surface of the Earth to the center of the moon is 385 million meters. This distance is large. Sorry, Kai? Sorry? Nope, that wasn't for me. Okay, never mind. So we want to find the gravitational field strength out here. So little g. Little g is equal to gravitational universal constant times the mass of the object creating the gravity, Earth, divided by the distance away you are from the center of this object. So big G is going to be 6.67 times 10 to the negative 11. The mass of the Earth is 5.98 times 10 to the 24, and I apologize for not leaving you enough space. We're going to divide that by the sum of these distances. The sum of these distances is going to be, if I add these together, 85 plus 6 is 91. So it's going to be 391,380,000 meters. And we're going to square that. So what is the gravitational field strength way the heck out there? Well, gravitational field strength, if I multiply this number by this number and divide it by that number squared, you're going to get, I'll give you the value for the sake of time, 0.0026 meters per second squared. That's a very small number. As far as gravitational field strength goes, there's not a lot of gravitational field out there. And the question is, Why, if gravity is so small out there, why does the moon stick around? Anybody want to take a guess? If Earth's gravitational field strength is 0.0026, why does the moon stick around? Sorry? Dwayne. What? Why? How are we going to figure out what the force is that Earth exerts on the moon? We take this little value g and we do what with it? We multiply it by the mass. This little, and what we multiply it is, or by, is the mass that of the object experiencing the gravity. So we're going to take this value, the gravitational field strength of the Earth, and we're going to multiply it by the mass of the moon, which I just so have happened to have given you on your formula sheet. The mass of the moon is 7.35 times 10 to the 22 kilograms. So even though the gravitational field strength is really, really small, the force of gravity is 1911, followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 zeros. Gravitational field strength is small, but the force of gravity on the moon is massive. To put that number into context, 1, 2, 3, boom, 1, 2, 3, boom, 1, 2, 3, boom, 1, 2, 3, boom, 1, 2, 3, boom. Okay, so that is million, billion, trillion, quadrillion. What's after quadrillion? Quintillion? 191 quintillion, 100 quadrillion newtons of force on the moon from the Earth. Just an incomprehensibly, stupidly large value. That, Dwayne, is why the moon doesn't go anywhere. Sire. Sorry? Yes, it's gradually getting by like centimeters per year, but yes, the moon is getting further from us. It's a great question. To answer that question, I'm going to tell you to flip the page. Let's briefly talk about satellites. And when I say briefly, I mean briefly. There's going to be no math on this page. Phenomenal question, Sire. So glad you asked it. Here we go. Given that the moon and the Earth are as far apart as they are, calculate the force of the gravity between them. We did this already. Let me write down for you what I just did. I said that Fg is equal to mg. The mass of the moon is 7.35 times 10 to the 22. We multiplied that by 0.0026. We found that that number is 1.911 times 10 to the 20 newtons. Just a ridiculously large number. So one way to answer that question, Sire, let's look at it this way. Why doesn't the moon get pulled into the Earth? So I'm just going to answer your question the other way. You asked why is the moon getting further away? I'm going to answer, here's why it's not getting closer. Here's how orbits work. You've got Earth right here in the middle, and you've got the moon way the frig out there. The moon at that location is experiencing a force inwards. But the moon doesn't stay there. If the moon was just stationary there, it would slam into the Earth. What's the moon doing? It's orbiting. What does that mean? It's moving tangentially. It's moving perpendicular to the force of attraction on the Earth. So it's moving this way. But if you have an object moving this way while something's pulling it in, what's going to happen? Well, you're going to get movement kind of over there, where the object is still being pulled in, but now instead of moving to the left, it's moving kind of that way. Well, and then you're going to get this, getting pulled in that way, but moving that way. So it's going to end up over here, still getting pulled in, but moving this way now. And it's going to go this way, but getting pulled kind of that way. So it's going to end up here, but moving this way. So over here, getting pulled in, but moving that way. And you see what's happening here. Because the moon is moving sideways, perpendicular to the force that's acting in, and this, how the moon got into this position is the source of a ton of debate. We don't know how the moon got where it is. It could have been a large rock floating by. It could have been something smashed into the Earth and it ejected our moon from the Earth's own mass. We don't know. We have no way of knowing. But at some point in the distant, distant past, this happened. A large rock was flying past our Earth, and the Earth said, I like you. You're going to stay. And the moon says, well, I have inertia of my own. I was moving. I'm going to continue to move. And the Earth says, okay, cool. You can move over there, but I'm going to still pull you this way. And I'm going to pull you this way, even as you move around and away from me. And that's what an orbit is. An orbit is inertia that is perpendicular to the force of attraction inward. This concept gets its own whole chapter. You will spend probably 2.5, 3 weeks on this if you take Physics 12 next year with Mr. Morrison. The unit is called Uniform Circular Motion. And it's all about how objects move in orbits around other objects. And now it's going to get a little complicated because, Sire, the full answer to your question is the movement of the moon around the Earth is not uniform. The moon has enough inertia to overcome this attractive force, and so it is slowly getting further and further away. And the further away it gets, the weaker FG gets. And so as it gets further away, it's actually able to move quicker further away. And so that's why the moon is actually getting away from us. Brad.
I was just wondering about like other planets just moving like closer to the isn't there like a thing like the sun?
So all of the planets are doing sorry?
It's like it has like so much like gravitational pull. That's the biggest.
So this is why we orbit the sun. Yeah. So the sun's moving through the universe, we orbit the sun. But so does Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. The sun is just so much more massive than anything else, and everything else is kind of spaced out to the point where because we're getting affected by Jupiter's gravity, but we're so far from Jupiter, and the sun is so much larger than Jupiter, that the sun is the dominant gravitational force in our solar system. But everything out that orbits the sun is affected by the sun's gravity. Does that answer your question? Okay. So, if you threw a football at different speeds it travels forwards. If you've ever thrown a ball, you've experienced this. But eventually, unless you're in a cartoon, the ball falls to the ground. If you're weak, it falls there. If you're stronger, it falls over there. But eventually the ball comes down. Because it doesn't matter how hard you throw it, FG is acting downwards. The entire time. But what if you threw it so fast? If you think back to our projectile motion unit, the horizontal velocity and the vertical acceleration are independent of each other. The vertical force of gravity does not slow the object down left and right. What if you were able to throw this ball so fast that it covered a horizontal distance that was great enough so that when gravity finally pulled the thing down, it actually missed the Earth? So you'd get this situation. The cannon is just going to get increasingly more powerful until eventually you are able to launch this thing horizontally so that as it falls toward the Earth, it constantly misses. And that's what an orbit is. It is a state of constant free fall where you are always missing the Earth beneath your feet. And so this is why we launch rockets horizontally. If you've ever seen a shuttle launch or a rocket launch, they don't go straight up. They go up at an angle. Because that's actually the optimized trajectory for I'm constantly falling. If you go straight up, and then you'd have to go over. But a rocket launch actually is sideways. You want to break the Earth while you are using the Earth's gravity to pull you into that circular path. So for those of you who hate the feeling of falling and have aspirations to be an astronaut, I'm really, really sorry to tell you, being an astronaut in orbit is feeling like you are falling 100% of the time. Until NASA says, fine, fall one last really good time, and we're going to land you back on the planet. Coming back down is just ending the free fall, which is kind of a really bizarre way to think about what an orbit actually is. This is all, as far as satellites go, this is as far as grade 11 is going to get, just to give you kind of a taste of this chapter coming up next year. Comments, questions, concerns about it? Sire, does that answer your question? Brad, does that address your question from earlier? Okay, cool. So these boxes down here, we're not gonna do it. Yes, sire. Yes. The reason that orbits are elliptical. Yeah. Oh, I've got to draw it on the board because I don't have any space on the page. Here's why orbits are elliptical. One of the reasons why orbits are elliptical. Here's the sun. Here's Earth. Well, we said that FG, we said two things. FG equals GMM over R squared. We also said that for every action, there's an equal and opposite reaction. So if Earth is experiencing an FG towards the sun, what does the sun have to be experiencing? FG towards the Earth. Because for every action, there's an equal and opposite reaction. So what ends up happening is, because the Earth is experiencing the force of gravity from, sorry, the sun is experiencing the force of gravity from the Earth, it actually wobbles a little bit. And so the Earth doesn't actually orbit the sun. The sun and the Earth together orbit a spot between them. And because Earth is as small as it is, the spot between the Earth and the sun is actually within the sun itself. But it's not at the center of mass of the sun like we would expect it to. If it was at the center of the sun, you would see a circular orbit. So what you have is you have an orbit that's not around the center of the sun. It's around the center of gravity of the two objects together, which is still within the sun but not at the middle. So when you get that, I don't think you do that. No, you don't do this in math anymore. You actually look at the equations for an ellipse. And so there's a point in space for these two where the optimized path is an ellipse. So there's a point of the Earth where it's furthest away from the sun, and on this side it's actually closer to the sun than on the other side of the sun. It's weird to think about. The math there is, I'll leave that for another day. If there's no other questions, then I'm done. But that's a good question. Dwayne. Yes. Is it possible? Is that what you're asking? Is it possible to throw the football with it? The harder you throw the football, the further it will go before gravity brings it down. But how hard you throw the football, but gravity pulling down does not have any effect on the horizontal velocity that you give the football. So as you crank up the velocity, it's going to get further and further away from you before it hits the ground. Is what I was trying to describe. That fixes that thing. Okay, I'm done. Yes, sir. Kale said no. Here you go. Here's what I want you to work on. Any questions you didn't get done from yesterday is you've got time to work on now because you've got about 20, 25 minutes till the bell goes. And I would like you to take a look at these 8 questions. Do I want you to do all 8? No, I don't want you to do all 8. I want you to do question 3. 6, 7, and 8. Question 1, 2, 4, and 5. These 2 are review of older concepts, and these 2 are review of older concepts. The idea that mass and weight are different. So if you want to go back and take a look at these 2, you can. But as far as the stuff that I've covered today, you're looking at questions 3, 6, 7, and 8. The last lesson in what? The booklet? No, there are lots to do yet. We got force of friction, we got tension, we got elevators, we've got ramps, we've got momentum, we've got springs. It's going to be great. We got lots of stuff to do. Okay, there you go. We're done with gravity, though. This is the end of gravity. You may use the washroom. No. You can go first. Okay, you've got your task on your mark. Say go.